The next question of lead code weekly contest 377 is maximum square area by removing fences from a field. So basically in this question we are given with n and m, where n tells the number of rows in the rectangular field and m tells the number of columns in the rectangular field. So okay, m tells the number of rows in the rectangular field and n tells the number of columns in the rectangular field, m and n. So basically we have some field like this. Initially, let's say it's completely open. Now, okay, the field size is m minus 1 and n minus 1. So there are m minus 1 rows and n minus 1 columns, we can assume. The field size is n minus 1, comma, m minus 1, comma, n minus 1. So this, okay, we'll measure it in terms of area. So we can say the field size is n minus 1 into m minus 1. This is the area of the field. Initially, it's an open field, let's say. Now, if we look at the columns, then we can assume that in the open space, the top left corner of the rectangular field is 1, comma 1, and the bottom right corner of the rectangular field is m, comma n. So basically, we have a rectangular field like this, where this is 1, comma 1, this is m, comma n. Now, on this rectangular field, we have some fences. Firstly, for sure, there is a fence around this field. That is, in the borders of the rectangle, there is a fence. That is at 1, comma 1, there is a fence, horizontal fence. Similarly, at m, comma 1, sorry, it's similarly at 1, comma n, there is a horizontal fence. And 1, comma 1, there is a vertical fence also. Similarly, at m, comma 1, there is a vertical fence. So this border fence is always there. Now we are given two inputs. That is, firstly, first array tells us all the horizontal fences that are present, apart from the first and last. So we can assume this is 1, 2, 3, 4, 5, so on till n, and this is 1, 2, 3, so on till m. We can assume. So these are the things there. Now we are given at which points horizontally, at which points horizontal fences are present. If 3 is given, then there is a horizontal fence like this. If 5 is given, then from 5 there is a horizontal fence, and so on. Similarly, if 4 is given, then there is a horizontal fence like this. There is a vertical fence like this. And if 5 is given, then there is a vertical fence like this. So in horizontal list, we'll be given with the points where horizontal fences are there. Similarly, one more list is given, which denotes the vertical fences in the rectangular field. So vertical fences, where at which all positions are vertical fences there in the rectangular field is given. So now we should say what is the now we are allowed to remove some of the fences. So we can remove any number of fences. Now we need to say what is the maximum square area that we can achieve if we can remove some random fences from this. So we should output the maximum square area. And one more thing, we should output the maximum square area. Once we find out the max square area, we should output that max square area by modding it with 10 power 9 plus 7. In case if no square can be found, then we should output minus 1. So this is what the question is. So we need to output the max square area. If we look at the constraints, n m and n can be in the range 3 to 10 power 9, and length of horizontal fence and vertical fences can be in the range 600, length of it. And values of horizontal fence can be in the range 1 to m, where 1 and m are exclusive. Similarly, vertical fences can be in the range 1 to n, where 1 and n are exclusive. As at 1 and n already there are fence, there is a border fence. Similarly, at 1 and m there is a border horizontal fence. So now let's see how we can solve this. According the if we look at the lengths of horizontal and vertical fences are very small, which is just 600. So it allows us to do brute force. So let's see how we can solve this. For that, let's pick a case. So if we look at this, let us take an example where m is equal to 7, n is equal to 9, and the horizontal fences are at 0.452, vertical fences are at 0.386 and 2. So if we construct all these, this is how the grid looks like, the rectangular field looks like. Now, if we observe, here we can make one observation. So basically, it is always optimal. It is always optimal to remove all fences and leave only two fences, or leave only one fence, right? Or leave only one fence, because uh, we can leave basically we can in the horizontal, among all the fences we can remove all the unnecessary fences, and finally uh, in the horizontal part, distance to the maximum, I mean in the horizontal part, length of side of square will be contributed because of two fences or one fence and the border fence, right? Because if we look over, if I remove this, then we can see that this part will contribute to square's side. Similarly, if I remove this, then we can see this part will contribute to the fence. So this part will contribute with respect to the border fence and so on. Right? So basically, if we bring down this observation to a easier one, then if we look this observation in a easier way, then it is just like we can form any horizontal distance, which is distance between any two horizontal barriers. Right? So basically, we can form a distance of 1 and 7. Similarly, we can form a side of length 7 and 5. Similarly, we can form a side of length 7 and 4. Similarly, we can form a side of length 5 and 2, and so on. Right? So that is because we can just remove all other barriers and leave out those barriers which are contributing to the side length. Right? So ultimately, what we can do is in the horizontal part, let us not look at with respect to this leaving two fences. We can just see that only two fences will contribute to the length of the side of a square. So now what we are doing is we are calculating all possible lengths of a side of a square that we can get horizontally, that we can get vertically using the horizontal bars. So it is nothing but we can just fix two horizontal bars and find out all distances, all lengths. So basically, if we see, all lengths that we can make are 7 minus, if I list over the horizontals, horizontal bars are these. So 4 minus 1, 5 minus 1, 2 minus 1. Similarly, 5 minus 4 is a possible length. Basically, all considering any two fences in this horizontal bar, including the edge fences, that is fence at 1 and fence at m, all possible distances that we can make in the horizontals, and all possible distances that we can make, all possible lengths that we can make in the verticals. So if we look over what are the all possible distances that we can make using horizontal bars, we can see that we can make 7. So if we just list out 1 comma 4 comma, so if I write these horizontal bars and 7, so I can make every distance by just fixing, like, to calculate distance we can just fix two things, and the difference between them will be the length of the side of a square that we can make, right? So ultimately we can say we can make 2 minus 1, we can make 2 minus 1, 4 minus 1, 5 minus 1, 7 minus 1. These are the distances that we can make, vertical side distances that we can make. Similarly, we can even make 4 minus 2, 5 minus 2, 7 minus 2, 5 minus 4 can be made, 7 minus 5 can be made, 7 minus 4 can be made, and 7 minus 5 can be made. So all these set of distances that we can make, that is, we can just fix two uh, 2 points and then calculate the distance or difference. That will be the distance vertically that we can make. Now, similarly, we can do it for vertical distances also. But for verticals, 3, 1 comma, vertical barriers are at 1 comma 3 comma 1 comma 2 3 6 8. So now for a for a square, the properties vertical distance and horizontal distance should be same. So now we can find out all distances that we can make vertically, and we know all distances that we can make horizontally. The max, the what is the, then we can just find out the maximum distance that can be made using vertical barriers and horizontal barriers, which is same. That will be the side length of side of the square using verticals and max distance using horizontals. So maximum distance present in vertical distances and horizontal distances, which is same, will be the side of the square, and in case no such side exists, then it's -1. So to calculate these distances, set of distances, we can brute force, run two loops I and j in horizontals and find out all the set of distances that we can make. Similarly, in verticals also find out all the set of distances and find out the maximum common distance. If there is no common distance, it's -1. Otherwise, answer would be side, maximum side into maximum side percentage mod. So find out this side, maximum side, then area of a rectangle, maximum length L, then area of a rectangle will be length of the edge of the square uh, into the length of the edge of the square. Basically, length of the edge of the square whole square. That would be the area. As we need to print it modulo mod, we can just output this L into L percentage mod. So time complexity of this would be big of n square, as we fix two loops and we iterate over. To calculate the distance, we fix two loops I and j, and then we calculate the distance in horizontals and verticals. So n square, in the sense, we can say it is length of horizontals square plus length of vertical square. Length of verticals whole square. So this will be the time complexity. Horizontal square plus verticals length square. And if you look at the space, we can implement this with a space of big of length of horizontals plus length of verticals. And it's even possible to optimize the space further, but this is sufficient for the given constraint. So this is sufficient enough to pass in the given TL. And basically we are maintaining the we are basically maintaining the differences, right? And to store the differences, we'll be using either map or a set to store them. Because we use either map or a set to search in them, there will be a log factor. So we can say this one into log 2 of length of h horizontals plus length of verticals will be the time complexity in the worst case. So this is per test case. So this is how we can solve the problem.